Okay, cool. So I guess let's talk about the materials today. So I guess last time we have talked about some of the kind of the bigger questions, the conceptual kind of bigger questions in deep learning theory. And today we are going to start talking about the optimization perspective in deep learning for one, maybe like for 2 lectures. So, and here, I guess I'm going to explain what optimization landscape means. It really means the surface, the surface of the loss function. So, but I guess you will see, so we are going to introduce some very basic things about optimization, but the main focus is actually not about how do you update, how do you design algorithm. The more focus is to analyze what the functions you are optimizing look like, so that you can use some trivial or some standard optimization algorithm for it. So so if you don't need any background about optimization, you probably need to know what gradient descent is. I'm going to define gradient descent again, but you probably need to know what algorithm is, optimization algorithm is, but there's no any kind of concrete requirement about the details, like what momentum look like, you know, what stochastic gradient descent is exactly is. You don't really necessarily have to know them. Okay, cool. So I guess the bigger the question we are trying to address, you know, just to quickly review, to connect to the kind of the last lecture, the bigger question we are trying to address here is that why many optimization algorithm, so many optimization algorithm are designed for convex functions, but why they can still work for non-convex functions, right? So why they can still work. And actually pretty well in practice for non-convex functions in deep learning. Note that it's not like these algorithms like gradient descent or stochastic gradient descent can work for all functions like that you may optimize, right? So definitely there are many functions that they cannot optimize there, and there are these examples in many areas of research. But in machine learning, typically, you know, people assume that you can, you know, people assume and also somewhat observe that you can optimize your function pretty well. Even though the function is non-convex. Of course, even in machine learning, there are atypical case or outliers, whatever you call it, especially if your parameterization of your model is very complex or kind of somewhat weird. So you could face some difficulties. For example, one simple example is that if you're you have a very deep network, like feed-forward standard deep networks, then it's actually pretty hard to optimize because sometimes you have vanishing gradients, sometimes you have exploding gradients, so on and so forth. So, however, some of these are solved by changing the architecture, which changes the landscape, the optimization landscape. Anyway, so the bottom line is that in most of the cases, people observe that non-convex functions in machine learning can be optimized pretty well by gradient descent or stochastic gradient descent or their variance. So, and we are trying to understand why we can optimize reasonably well. So that's the question. And maybe just before talking about more details, let's first quickly review the kind of like what gradient descent is, right? Just in case this is very quick, I'm just going to define some notations here. So suppose g theta is the loss function. I guess I'm using g here just because you know, I want to use a generic letter instead of just instead of use L, right? So L probably should be a better letter, but here I'm using something that is more generic. So, and the algorithm is just something like set 0 is some initialization, and you have something like theta t plus 1 is equals to theta t minus eta times the gradient of g of theta t, right? This is gradient descent. And you can have stochastic versions of it. Many of you probably know them. So, and I'm going to list a few facts, you know, just to kind of motivate the discussions here, right? So when we're looking at non-convex functions, maybe let me draw a non-convex function, something like this, right? So, and the first fact is a fact, or it's just you know, some observation. So maybe let's call it observation. The first observation is that so GD cannot always find global minimum. Right, this is for continuous functions, right? This is kind of obvious because, depending on where you initialize, depending on like how the function look like, for example, in this case, suppose you initialize here and gradient descent will go rightward, and maybe it overshoots a little bit and it go back, so on and so forth. But then at the end of the day, it converts to this local minimum, right? If your learning rate is somewhat small. Right, so it was stuck at this local minimum and stay there. And even you have stochasticity, if your stochasticity is not big enough, you are not going to go to another local minimum, go to the other global minimum, right? So clearly you cannot hope that gradient descent to work, like in the worst case range for all possible non-convex functions, right? So observation 2. Actually, this is a theorem. So finding global minimum of general functions, general non-convex functions, is NP hard. Is NP hard. I assume some of you have statistical backgrounds who are not exactly familiar with NP hard. It doesn't really matter. This is just really saying that it's computationally intractable to find global minimum for but just to clarify, what does that mean? That means that there exists a function that you cannot solve. It doesn't really mean that for so basically this is only saying that you cannot in polynomial time solve all possible functions with gradient descent or with any algorithm. But it doesn't really mean that there's no subset of functions that you can easily solve, right? So for example, a convex subset of functions can be solved in polynomial time. Okay, so and the observation 3, obviously this is opposite observation. So gradient descent can solve convex functions, as I said. And I guess observation 4 is that objectives in deep learning is non-convex. This is probably not entirely trivial. It's almost trivial, but not entirely trivial. So you have to, it's probably kind of trivial to see that you cannot prove that they are convex, but you probably need a little bit kind of calculation or some kind of constructions to see they're not convex. And generally, they are not convex just because there's so many nonlinearities, and most of the convex functions we know are somewhat kind of like simple functions as a linear function composed with a convex loss, for example. And as soon as you go beyond 2 layers, you have it's not convex. Okay, so and observation 5, I think this is what I mentioned it. So like gradient descent does work. Gradient descent or stochastic gradient descent does works. So finds. Let me be precise about this. Finds approximate, or even sometimes you can claim it's almost exactly global minimum of loss functions in deep learning. Of course, this is not like a 100% rigorous statement because it depends on which loss function you are talking about, what data set you have, and what architectures you have, so on and so forth. But I'm just saying, like, for most of the cases in deep learning, stochastic with standard gradient descent seems to work pretty well. And why they are finding the global minimum? So that because the loss function is non-negative, right? So suppose you run ImageNet or you do some kind of like a Bayesian experiments, and the global minimum has at least the loss function is always non-negative, and you can see how small the loss SGD or GD can get you, and often the loss function is pretty small, something like 1e minus 2 or something like that, or maybe sometimes, depending on whether you use regularization, sometimes it could be 1e minus 4, 1e minus 5, depending on the situation. So you kind of believe that you get at least an approximate global minimum. Cool. So what's going on here, right? So it sounds like this, there are some positive results, empirical observations. There are some negative results about the NP hardness or the intractability of the of optimizing non-convex functions. So the way that that can reconcile this is really just that, the lower bound, the impossibility results is about worst case functions, and actually we are not optimizing worst case functions, right? So I guess the kind of, in my mind, the kind of view is that you have a family of all functions, right? So in this family, there are functions that are super hard to prove, super hard to solve, right? So like very hard functions. And there's also a small subset of functions, let's call it convex functions, right? These are not we call it convex functions. These are just convex functions, and these are easy to solve, right? So Green descent can solve them. But actually, we didn't identify all the functions that we can solve, right? There are actually more functions than convex functions that gradient descent or some other algorithms can solve, and that's a slightly larger family in between. And today we are going to talk about this kind of functions, right? So of course we cannot identify all the functions that are benign enough for us to solve, but we are going to identify a subset of the bigger than convex, the convex subset, right? So these are non-convex, but somewhat have benign properties. Some benign properties, and the kind of the task is to figure out what properties that make them somewhat nice and easy to optimize. All right, so so here's our plan for this lecture and maybe the first part of the next lecture. So the first step is that we're going to identify a large set of functions, a larger set of functions that SGD or GD can solve up to global optimality. And two, we're going to prove that for some special, some of the loss function in machine learning problems can belongs to this set, belongs to this set we just identified, right? This larger set of functions we just identified. And most of the so most of the effort will be spent on the second bullet. The first bullet, you do need to show why SGD can solve this set of functions, but I guess I'll tell you what people can show in the first bullet, along the line of first bullet, but I wouldn't tell you anything about all the details. The results there actually is in some sense kind of like intuitive. So but they do require a lot of backgrounds to talk about the details, right? So like you need to know like a lot of things about how to analyze this iterative optimization algorithms. So that's why we don't focus on that. We mostly focus on the second part, which is more about the statistical properties of those functions used in machine learning. Okay, cool. So the very basic idea is the following. So it's very simple. So basically you say that so you know that gradient descent can find local minimum. This is somewhat easy to believe, but actually there is some caveat about it. Maybe I'll put a star here just to remind you there is a caveat, but you kind of believe that roughly speaking, gradient descent can find a local minimum, right? And suppose if you know in addition that all local minimum of F are also global, then this too means that GD can find global minimum. Right. So basically, the first statement is about the first. So basically, the set of functions that we are going to identify to be solvable by GD and SGD is just a set of functions with with the property that all local minimum are also global minimum. And then we need to characterize, we need to show that, the functions we are actually using in machine learning have this property, right? Of course, not all problems have this property, we're going to show some very actually simple cases where you can prove this. Okay, so, but I guess as I mentioned, there's some caveat about whether you can even converge to a local minimum. So this is actually somewhat nuanced. So, and I want to be kind of like as clear as possible about that. So I'm going to formalize this, converging to a local minimum, but I'm not going to prove any of the theorems here, right? So next part is about convergence to local minimum. Right, so I guess let me start with some definitions to formalize it. So let F be twice differentiable. Just for simplicity, we are like sometimes you can extend this to maybe like only differentiable, but not twice differentiable. But just for simplicity, let's say F is twice differentiable. And what's the definition of local minimum? I guess you have seen this in calculus class, right? So X is a local mean of the function F if there exists an open neighborhood let's call it N around X such that in this neighborhood N, X, the function value I'm using a lot of text here just to make it easier to understand. Alternatively, I can also use just math. But let me use the text. So in the neighborhood N, the function values, all the function values in neighborhood N are at least fx. Right. So basically, fx is literally one of the minimum in this neighborhood. So that's the definition of local mean. And so I guess, from the calculus class, you probably know that, if X is the local mean, it means that the gradient of fx is 0. The gradient square of the Hessian of f is PSD. Okay, so these are necessary conditions for being a local minimum, but not vice versa, right? So it's not like if the gradient is 0 and the Hessian is PSD, then you are a local mean, right? So why? I guess a simple example here I came up, it's easy to came up is that you just say maybe, actually I'm not taking the simplest one just for some reason because I'm going to use this again. So let's say suppose you have x1 f of x1 x2, which is something like in the x1 squared plus x2 cubed. Okay, so and in this case, x1, x2 is 0. The origin satisfies the gradient 0 and satisfies the Hessian is PSD. Actually, the Hessian is 0, right? So that's why it's PSD, right? Just because if you take the second order, wait, the Hessian is not 0. Sorry, the Hessian is PSD, right? Because the Hessian is a matrix. I guess in one direction is 2, and the other, all the other things 0 is PSD. Okay, cool. All right. So but X is not a local minimum, as you can see, right? Because if you change x2, you can make the function value smaller in the neighborhood, right? Right, because x2 is the cubic function, right? So you can always make it smaller than 0 in the neighborhood of 0, and in the neighborhood of 0. Okay, so so basically, from this example, you can kind of see that what happens is the following. So why this is a problem, right? So fundamentally, what's the problem here? The problem is that when the gradient of fx is 0, and also the Hessian is not strictly positive semi-definite, it's just a positive semi-definite. So suppose Hessian vanishes in some direction. Right, so if Hessian vanishes in some direction, and so that means that in that direction, you don't have the first order gradient, you don't have the second order gradient. In that direction, you're pretty flat, right? So that makes it tricky because then the higher order gradient start to matter. Derivatives starts to matter, right? Because if your second order derivative is actually non-zero, it's curved, then the third order derivative is always killed by second order derivative, as long as your neighborhood is small enough. However, if your neighborhood, but if your second order derivative is literally zero in some direction, then the third order derivative starts to matter. So that's why, local minimum is not only always a property of the first and second order derivative. So, and when you look at this, and once it becomes about the third order derivative or fourth order derivative, things becomes much more complicated. And actually, if you look at the hard instance, of the NP hardness or the intractability results about optimization. So once you are, so basically all the hard cases happens when you have to deal with the higher order derivatives, like fourth order derivatives. And then basically in the, I'm not sure, I know this is probably not making that much sense for all of you if you're not familiar with the how you prove NP hardness, but basically you can embed hard instances of the like some kind of like a set instance to the fourth order derivatives, so that knowing whether the fourth order derivative is positive is a positive operator is equivalent to knowing whether you solve the set problem. Anyway, so this is only for those people who know a little bit about the computational intractability results. Anyway, but the intuition is that higher order derivatives is just hard to deal with, especially higher than fourth order. And there's a theorem which is the following. So the theorem is that verifying if X is a local minimum without any assumption of the local minimum of F is actually NP hard. So that finding a local minimum is also NP hard. So I've told you that finding a global minimum is NP hard, but actually finding a local minimum is also NP hard. And this is this is the caveat I was referring to, because in most of the cases, if you talk to somebody right now, like if you talk to me about research, in a meeting, we'll think about finding a local minimum is easy, right? In general, that's the right intuition, but it's not exactly true, right? So you have to consider this kind of pathological cases, which makes things harder, right? So how do we proceed, right? So if finding a local minimum is hard, then this plan doesn't work, right? So the way to go beyond it is that there is a way to also remove some of the pathological cases as well, so that you can find a local minimum in polynomial time, and then we can execute our plan. Right, so this is what will happen. So so here is a condition called strict saddle condition, and if you satisfy the condition, then you remove those pathological cases which requires higher order derivatives. So sorry. Strict saddle condition. So let me. So in some sense, I guess I'm not sure whether this makes sense before I define it, but generally you are basically saying that you want to rule out. You want to say that you assume your function doesn't have this kind of like somewhat subtle possible candidate of local minimum, right? So every point, whether it's a local minimum or not, can be told from examining only the first order gradient and the second order derivatives. So there's no subtle cases in your function, right? So how do we formalize this? This is strict saddle. I guess the paper to cite is Li et al. By the way, I think I wrote a book chapter about this kind of optimization thing for a book, so I can send that to the person who take the scribe note, and that probably help you to have some references. But the materials are not exactly the same as the book, so you still have to do do the scribe, kind of from scratch in some sense. Okay, okay, cool. So the definition of strict saddle, this is I'm citing this paper just because it's not like every paper use exactly the same definition. The very original paper that introduced this term and this notion is called by Rongge and et al. So in 15, so that paper has a slightly different definition. But I think this one, the definition Li et al. is a little bit more kind of like easier to use for the future research. So I think people are somewhat converging to this. So we say, so here's the definition. So we say F is alpha, beta, gamma strict saddle. If for every x in RD, every x in RD satisfies one of the following. So the first one is that, for some of the x, it just satisfies that fx, the true norm of x is larger than alpha, right? So you see that, of course, some of the x satisfies this, right? So your gradient is big, so these points are not local minimum, right? So these are not stationary point, they are not local minimum. Okay, by the way, by stationary point, I mean first order stationary point, meaning those points with gradient 0, right? So if you satisfy number 1 here, you cannot be a local minimum, you cannot be a stationary point. And the alpha, beta, gamma are positive numbers. And the second thing is that the lambda mean of the Hessian at x is less than minus beta. So if you satisfy this, you cannot be a local minimum, right? Because your Hessian is not positive semi-definite, right? So you cannot be a local minimum. And in some sense, you can think of alpha, beta, and gamma to be something super small or even close to be 0. We just require them to be strictly bigger than 0 just for technical purposes. So basically, the third condition is that x, the third possibility is that x is gamma close to a local minimum. To a local mean. Let's call it x star, and in Euclidean distance. The distance metric here probably not entirely important because we are not going to be very quantitative about this. So everything is polynomial, so it's not that important. So basically, this is saying that if number 1 rules out some kind of like local minimum, number 2 rules out some other kind of local minimum. But note that number 1, number 2 doesn't rule out all possible local minimums because there are even local minimum which has gradient 0, which has 0 gradient and positive semi-definite Hessian. So they're also, my bad. So 1 and 2 doesn't tell you exactly whether a point is local minimum per se if you don't have this assumption, because you can have a point that does not satisfy 1 or 2, right? For example, if you have a point with gradient 0 and Hessian is PSD, right? It doesn't satisfy 1, 2, but it could still be not a local minimum, right? That's the pathological case. And this assumption, this definition, is basically saying that if you don't satisfy 1 and 2, then there's no this pathological case. You have to be close to a real local minimum, right? So that's what this strict saddle condition is saying. Maybe let me pause for a moment, see whether there's any questions. Actually, I'm looking at the query board. I know it's open, it's empty, but if you have any questions, feel free to ask. Yes, alpha and beta are positive. Yes, that's right. So this definition only makes sense when alpha, beta, and gamma are positive. I think, right, yes, exactly. So alpha, beta. Any other questions? The third strict saddle condition sounds hard to check. Yes, that's a great point. So you cannot check. There's no way you can check whether empirically your function is satisfies this condition. So I think it's even. I'm not 100% sure about this, but I think you can prove that if you are just giving an arbitrary function, right, differentiable functions, you shouldn't be able to check whether it satisfies strict saddle, right? It should be as hard as finding a local minimum in some sense, right? So this condition is not supposed for, is not something that you are supposed to check numerically. This is something that you are supposed to prove theoretically in some sense. If you can, of course, I know in many cases you cannot, like not you cannot, but like nobody can do. But I think the condition itself is not supposed for people to numerically check. That's a good question. Okay, cool. So, and by the way, always feel free to ask questions, just even as I'm speaking. Okay, cool. So let's see. Okay? We have the condition, right? So now, what you can do with this, right? So, so here's the theorem. The theorem is somewhat kind of like informal, just because I'm not, it's pretty formal in the sense that all the bounds are correct. It's just that I wouldn't specify exact some of the details. So suppose f is alpha, beta, and gamma strict saddle. Then many optimizers, for example, GD, SGD, if you use the learning rate correctly, and there are many other algorithms like cubic regularization. I guess many algorithms can do this. So so and so forth, can converge to a local mean with epsilon error in Euclidean distance. In time poly D is dimension 1 over alpha, 1 over beta, 1 over gamma, and 1 over epsilon. Right, so this theorem is very coarse-grained. Of course, different optimizers have different convergence rate, but we are not, at least for the purpose of this course and this lecture, we are not interested in which one is faster. We are mostly just interested in whether it's polynomial time versus exponential time. And the point is that if you have the strict saddle condition, then you can converge to a local minimum. You don't have those pathological local minimum pathological cases. Then you converge to a local minimum. You can converge to a local minimum in this Euclidean distance in this polynomial time. All right. Okay. So by the way, I think just to explain the name of strict saddle, I think this is just because the pathological case is a saddle point, right? So when you have this kind of like cases where the gradient is 0 and the Hessian is PSD, but not strictly positive semi-definite. So you have some direction where you can potentially have a negative curvature, like you can potentially have a flat curvature, but potentially you can have like bad third order derivatives, and these are kind of saddle points. So this is in some sense that explains the name for this, right? So in other words, the condition is saying that if you are a saddle point, you can tell that it's a saddle point from the negative curvature. what is the third optimizer inside the parenthesis? That's a good question. This is called cubic regularization. I guess there are so many others. Cubic regularization is one of the early work in 2006 by Nesterov. But there are many other optimizers. Like I published a paper on this. Like many other papers. Like many other people publish papers on this. I think. I can add more references in the scrap notes, in the final scrap notes to cite some of the recent works. Yeah. So, right. Okay, cool. So, all right. So, and now we can converge to local minimum with this condition. And now suppose you make additional assumption to say that all the local minima are global, then we are good, right? So basically, the next theorem is trying to say that are global, and you have the strict saddle condition. Then this means that the optimizers can converge to global mean. Right. So here is a theorem that formalizes this. I guess I'm writing it a slightly different way, not because just in some sense I unpack it a little bit. Just I thought that this is either provides a slightly different way of thinking about this, or it's just a more explicit. So basically, you say that you assume the strict saddle condition, but let's rephrase the all local minimum global plus strict saddle condition like this. So you say that there exists epsilon 0 and tau 0 and C such that if X in RD satisfies the gradient is small than the epsilon, and the Hessian is larger than minus tau 0. So basically, this is like what does this two condition means? This is saying that you are a somewhat approximate local minimum, right? So you have already passed the sanity check for local minimum, right? But you of course you haven't passed the you cannot rule out the pathological cases, but at least you pass the first order condition. The first order gradient is small. You somewhat pass the second order condition approximately because the Hessian is somewhat big, almost kind of larger than 0. And then this is saying that suppose you pass these two conditions, then X is epsilon to the power C close to a global minimum. The power C is just like to relax the condition so that you can have square root epsilon, for example, close, something like that. So then X is close to a global minimum of the function f. Right. So this condition is just a slightly different way to say that you have all local minima global and strict saddle together. All right. So and then under this condition, then optimizers, again the same set of optimizers which can converge to local minimum. Many optimizers can converge to a global mean of f up to say delta error and Euclidean distance in time Pauli 1 over delta 1 over tau 0 and d. All right, so it's not exactly stated the same as we did for the strict saddle, but if you think about it, it's basically the same statement. Okay, anyway, so cool. So we are basically done with the first part, right? So like about the identifying the subset of functions that are easy to optimize, right? These are all local minimum, global minimum functions. So and next we are going to show some examples where this kind of properties can be proved rigorously for machine learning situations. But these examples are pretty simple. They are not deep learning, right? So these are still roughly the best people can do, in some sense. So so this is just to give some examples for which this kind of properties can hold. Okay, so next we have two examples. So the first one is the PCA on matrix factorization. And fundamentally, this is more or less the same as the linearized neural network. Even though if you do linearized neural network, there is a little bit more things to do beyond that. And the second example I'm going to give is matrix completion. This is a important machine learning questions, by itself as well, right? So before deep learning, this was, one of the most important topic, maybe machine learning, like especially nonlinear. If you think about nonlinear cases, and now still I think it's used in recommendation system. So we're going to talk about that. Okay, cool. So any questions so far? I guess let's talk about PCA. Okay. First, so I guess or maybe more precisely matrix factorization. So we are assuming that we are given a matrix M in dimension d by d, and you want to find the best. Let's talk about the rank 1 case, right? The rank 1 case. So we want to do the rank 1, best rank 1, rank 1. So best rank 1 approximation of the matrix. I think probably from other classes you have know that the best rank 1 approximation is basically the kind of the eigen decomposition or the singular value decomposition of the matrix. Here, let's also assume, just for simplicity, let's also assume this matrix M is symmetric. Let's also even assume it's PSD, just for simplicity. So in this case, the best rank 1 approximation is basically the eigenvector times the eigenvector transpose, right? Up to some scaling. So so this is not a hard problem, right? So you can just run any eigenvector solver to find the eigenvector and then scale it properly, then you get the best rank 1 approximation. So but just for the purpose of this class, we are interested in this non-convex objective. Function, right? Which is like a literally, like interpreting this in the most straightforward way. So you say, I'm just literally finding this best rank 1 approximation. I know the best rank 1 approximation should be symmetric. So I'm just trying to find let's find a vector x such that M minus XX transpose in Frobenius norm is the smallest, right? So you are approximating M on the matrix M with the matrix XX transpose, right? So XX transpose is the rank 1 approximation, and you match the error by Frobenius norm. Okay, so and this becomes a non-convex objective function because you have a quadratic term here, and then you take the square of that, it becomes like degree 4 polynomial, and it's non-convex. Right. So so and our goal is to show that even though it's non-convex, like all local minimum of this G are global minimum. Under the assumptions that we have mentioned, right? So like rank 1, PSD, so on and so forth. Okay, so I guess, I think I forgot to pass a figure here. So if you look at the one-dimensional case, this function looks like this. So one-dimensional. So D is 1. So D is 1. Then you just have a scalar m minus a x squared. This is a function, g of x. And you plot this function looks like this. And there are two local minimum, and they are both global minimum because there's some symmetry here. And if you have like a higher dimensional, it becomes a little bit more complicated because you have actually not only necessarily, in some cases, not only necessarily one, like not necessarily only like two local minimum. Or I guess if it's rank 1, there are only two local minimum, and but it looks more complicated. But generally, you have some kind of rotational kind of symmetry here to make this happens. Okay, so let's talk about the proof, right? So how do we prove this? So as you can imagine, the proof is pretty simple. The plan is very simple. You first find out all stationary points, the first order stationary points. And then you find out all local minimum. And you prove that they are all global minimum. So basically, it's just more or less like we solve all the equations of the solve all of these equations and see what are the possible local minimum you can have, right? So let's first use the stationary point, the gradient condition, right? So gradient of x is 0, and what is the gradient of g of x, right? So gradient of g of x, I'm not going to give a detailed calculation here, but believe me, this is equals to minus this times x. I think this is actually a question in homework 0, maybe question 2 or question 3 in homework 0, about how to compute a gradient. So, and you have the gradient, and then you say, let's write out what is 0 means, right? So this means m times x is equals to the 2 norm of x squared times x, right? Because the three things together, the last two things becomes the 2 norm of x squared, and that's a scalar. You can switch the sign, you get 2 norm of x squared times. You can switch the order, you get this. Okay, cool. So and this is a scalar. And this is a matrix vector multiplication. So basically, this is saying that x is an eigenvector, right? So x is eigenvector, and x squared corresponds to eigenvalue. So basically, you have to, maybe one way to think about this is that you first find out the unit eigenvector, right? So the eigenvector doesn't have a scale, right? So you first find out the unit eigenvector. Let's say the unit eigenvector are v1 up to vd, and then if you have unique eigenvectors, then so suppose, let's say, let me just specify this. So this part just is for some intuition. So suppose eigenvalues are distinct, even though we don't have to assume this. Then you have unit eigenvector v1 up to vd, and you have lambda 1 up to lambda d. And these are the eigenvalues. And then basically all the stationary points are of the form that x is equals to plus minus square root lambda I times the eigenvectors, right? Because if you measure the norm of x squared, then you get a lambda I, and that is the corresponding eigenvalue. Right, so these are all the stationary points, the first order stationary points of this problem. And now let's look at which of these is global minimum, is a local minimum, and then we say, okay, all the local minimum are global, right? So ideally, we just want to say that only the VI, the V1 thing is the local minimum, right? Because that one is also a global minimum, right? So lambda 1 V1, square root lambda 1 V1 is the global minimum. Okay, so how do we do this? So, and also we don't necessarily want to assume all the eigenvalues are distinct. So there's a small things to be done regarding that as well. So, so let's compute Hessian, right? So we need to use the Hessian. So I think, this is actually a typical question I got, when people start to think about this kind of like optimization problems, because and the typical question is that how do you find the Hessian? How do you write out the Hessian sometimes, right? The Hessian sometimes could be very hard to be written down. So here it's actually not that hard because the Hessian is in dimension d by d, because you have d parameters. Sometimes your parameters is a matrix, and then your Hessian becomes a fourth order tensor, and it's kind of very complex to be even just written down to just write down the Hessian. So here is a kind of a very useful trick, and which actually also has some fundamental reasons that this is useful. So so the useful thing is that if you look at the quadratic form regarding to the Hessian, right, you look at V transpose Hessian V, or V in the product with Hessian times V. This is the quadratic form related to the Hessian. This is much easier to compute. So why this is much easier to compute? Because the methodology is the following. So this is in some sense in the homework solution of that homework that asks you to find the gradient of this of this function, right? So I guess we have the homework. Homework 0 has this question to ask the gradient of this function. The same methodology also applies here. So when you talk about the Hessian, so the methodology, I'm not going to go to all the details, but the roughly speaking, what you do is the following. You say, I'm going to consider gx plus epsilon, right? So I'm going to Taylor expand this. So I'm just going to iteratively Taylor expand it. Whatever this g is, right? G needs to have an analytical form. Maybe it's a composition of several functions. You just iteratively expand it. Taylor expand it so that into something like g of x plus some epsilon times some vector plus some epsilon times some matrix. So okay, I guess maybe I shouldn't even write this. So g of x plus some linear term in epsilon, plus some quadratic term. And so on and so forth, right? Plus higher order term. And then if you have this, then this basically corresponds, if you replace epsilon to V, replace epsilon by V, then you get V dot G square GX V. So I guess I'm not sure whether this is too abstract, when I say this, but if you are you didn't get exactly what I mean, so just look at the homework 0 solutions. It's basically doing this. So so this is a very simple way to compute the Hessian, the quadratic form over the Hessian, without writing the Hessian as a complex matrix or tensor. So if you apply this kind of techniques, you can get the Hessian like this. So the quadratic form of the Hessian is equals to something like this. So I guess you can see that here I'm not writing it. I still don't necessarily have exactly a representation or a characterization of what the Hessian is, right? I'm only writing the quadratic form as an analytical formula of x and m and v, so on and so forth, right? So you can, in this case, you can still, from this quadratic form, you can figure out what the corresponding matrix is, right? You can write it as a matrix multiplication. That's okay. But for many other cases, actually, it's very hard to write out that matrix of the Hessian, right? But the quadratic form is just some analytical formula. And as you will see, actually, the only thing that matters is the quadratic form, because anyway, even you are giving for example, a Hessian, which is kind of complex, there's not much things you can do with it, right? So pretty much you're still looking at the different specific quadratic form. Anyway, okay, so we have this quadratic form, and we know that the Hessian is larger than 0 is equivalent to that for every v, the quadratic form of the Hessian is larger than 0. Okay, so here's what I mean why you only care about the quadratic form. This is just because you only care about basically if you plug in different v's, you get the same thing. And but which v we want to plug in? Shall we plug in all of the v's, or shall we just use some specific v's? It turns out in many cases you only care about a few special v's because some of the v's are much more informative than the others. And which so you want to choose some informative v's to evaluate this formula so that you get some important information about what x can be, right? Because at the end of the day, you care about what x is because you are using this to pin down what are the local minimum. So what are the informative v's? So it turns out that the v's that are informative here is the top eigenvector. How do you know this? It requires some intuition, it requires some trials and errors, so on and so forth. But I guess it also probably makes sense because the top eigenvector direction is the global minimum, right? So you somehow you try whether you can move in the direction of the global minimum to see whether your function value can increase in a second order sense. And to some extent it's intuitive, to some extent it's just the trials and errors. So but anyway, so v is equal to v1 is a good choice because if you plug it in, you get v1 times the Hessian of x times v1, and you plug into this formula, you get 2 times x v1 squared minus v1 transpose m v1 plus x2 norm squared. And you say this is larger than 0. And you can probably see why this is informative because this term is negative, right? So it makes it's the hardest test in some sense because the negative term is maximized. So and now let's look at what we can get from this equation, right? So realize that we don't care about the Hessian for every point, right? So we only care about the Hessian for the stationary point, the first order stationary point, because only those points can be possibly a local minimum. So we only look at x is an eigenvector, right? Because we are only filtering local minimums from the stationary points. So because x is an eigenvector, we have two cases. So the first case is that x has eigenvalue lambda 1. So x has the top eigenvalue. Then x is just a global minimizer, and we are done. Because we know the the global minimum is basically using the top eigenvalue to fit, right? That's by the standard results in PCA, you know that the best of one quantum approximation is the top one eigenvector with the right scaling. So the second case is that x has eigenvalue, let's say lambda, which is strictly less than lambda 1. So it could be the second eigenvalue, it could be the third eigenvalue, so on and so forth, right? So and then because x is an eigenvector, and also the eigenvalue of x is orthogonal to the eigenvalue, sorry, the eigenvalue of x is different from the eigenvalue of v1. So you know that x is orthogonal to v1 because different eigenvectors with different eigenvalue will be orthogonal. There's no guarantee that two eigenvectors are always orthogonal, because they could have the same eigenvalue and they are just in the same subspace. But if they have different eigenvalues, then they have to be orthogonal. So that's why x1 is orthogonal to v1. And then if you evaluate 2, this equation 2, so 2 means what? So 2 means that the first term goes away, so you get just x2 norm square is bigger than v1 transpose m v1. And I recall that the v1 transpose m v1, this is just lambda 1, and x2 square, recall that that's equals to lambda. I recall that's by the first order condition, you have that here the x2 norm square is the scalar that corresponds to the eigenvalue of that vector. So basically, we have lambda is bigger than lambda 1, and we have a contradiction because this is contradictory with the assumption that lambda is less than lambda 1, right? So right there. Okay, any questions about this? So guys, maybe just a very quick summary. So So basically this is saying that if X is stationary, by stationary point always means first order stationary point. So I'm not going to clarify that in the future. So if X is stationary point and X is not local mean, and if X is not global mean, then moving in V1 direction. So moving in V1 direction doesn't really, wouldn't change your function value much, right? Because you are a stationary point, that means your point is flat. So changing in V1 direction wouldn't change it by a lot. It would only lead to a second order improvement. And that's why it's not a local minimum, right? Because if you are local minimum, moving in a V1 direction shouldn't give you any second order improvement either, right? So so that's basically the gist of the analysis. All right, so cool. So I think we have to talk about, okay, so now let's talk about matrix completion, which is kind of like an upgraded version of PCA. And as I said, this is actually a pretty important question in machine learning. So let me define the question first, and then I can briefly talk about why people care about it. So let's also talk about the rank 1 version just for simplicity. So the question is that, so let's say suppose, and also we are assuming that we have, I guess we assume the ground truth matrix M is also a rank 1 matrix. Let M be a rank 1 matrix. And symmetric and PSD, just for simplicity. And so in other words, you can assume M is equal to something like ZZ transpose, right? And Z is the kind of the ground truth, and Z is in direction D, dimension D. And the setup is the following. So we are given random entries of M. So you pick some random indices of M, and you review the corresponding entries. That's the only thing you know about M. And then the goal is to recover the rest of the entries. Right. So so more formally, so you say that there's omega, which is a subset of the entries, subset of the indices of D times D, and you say this is actually a random subset in the sense that every entry is chosen, is included in omega uniformly randomly. It's included in omega uniformly randomly, independently with probability P. Okay, so each entry is included with some probability P, and you review. So what we see, we observe the so-called P omega of M. P omega of M is basically, okay, so let me define P omega of M. So P omega of A is the matrix obtained by zeroing out every entry outside omega. So you get this matrix A, and everything that is not in omega, you make those entries 0, and you are given this sparse matrix P omega of A. So we observe P omega of M, and our goal is to recover M. And why people care about this question a lot, in the past, one reason is that it has this relationship with recommendation system. So so here I'm assuming it's a symmetric matrix and so on and so forth. But if you relax those a little bit, which doesn't necessarily change the essence of the problem. So suppose you think of have a matrix, and in one side you are the columns are indexed by the users. So let's say suppose this is a matrix that Amazon maintains, and the other side is the item, and each entry is the rating of the user to the item. So it's a and every user probably have an opinion about every item, right? Either they like it or not, so on and so forth. But it's not like every user buys every item, right? For sure. So every user only buys a very small subset of the item, and that's why you only see some entries in this matrix, right? Amazon only sees some of the entries, and Amazon wants to understand each user's preferences. Want to know that each user likes which item, right? So the Amazon has an incentive to just fill in the entire table. Right? I'm just only using Amazon as an example, but the same thing probably applies to many other situations where you have to recommend items to users. So that's why you have to recover all the rest of the entries to serve the users better in the future, and that's why this problem was important. It's still kind of important these days, but I guess there are many already existing methods to solve this, and the most used method to solve this is basically non-convex optimization to find this best this ground truth matrix M. Using the fact that you have a low rank structure in M, right? Because how come you can recover the rest of the entries? If there's no any structure in M, in this matrix M, there's no way you can recover the other entries because they can be arbitrary. So that's why you have to assume that the matrix M has some low rank structure or some other structures. So maybe just to give you a quick kind of like sense about how does the structure matters here, right? So we have, if you count the number of parameters, we have D parameters, right, to describe a rank 1 matrix of dimension D by D, right? Because you can just write it as X transpose, and how many how many entries you observe should be probably bigger than the degree of freedom here, right? So the number of observations is roughly equals to P times D squared, right? Because each entry is observed with probability P. So you have P times D squared entries, and this should be bigger than D, right? If this is not bigger than D, it's unlikely you can work, right? So basically, that is saying that P is bigger than roughly 1 over D. And this is actually the regime we are going to work with, right? So we're going to work with the regime that P is much bigger than 1 over D by for example, log factor, something like that. So that's the setting we are going to be in. And speaking of the objective functions, this is actually a pretty commonly used method in practice. So you just say, I'm going to minimize this function that's called fx, which is defined to be that you have a parameterization called xx transpose. This is your target. This is the parameterization of a target matrix, and you want to say this matrix actually fits all my observations, right? So you are taking a sum over all possible observed entries because these are the only cases you know what the entries are. You know those mij, and you minus this with xi times xj, and you take the square. So this is your prediction, this is your observation, and you take the square and take the sum over all the observation, all observed entries. And just for future notational easiness, so this is actually, you can write this as P omega of I minus XX transpose, right? Because this is the matrix, you look at the error matrix, right? And then you zero out all of those that you don't know, right? Because outside omega, you have no information, you zero out all of those, and you take the sum of squares of the rest of the entries, right? So that's another way to write this function, right? So, and just a side note, I think actually there are many other methods that can solve matrix completion. So there are convex realization methods and so on and so forth, right? So However, those methods actually often have stronger guarantees. For example, they have tighter sample complexity bounds, so on and so forth. But in practice, just because the convex transition takes too long time, people actually are using objective functions or methods like this, and then they just use gradient descent to optimize these kind of functions. And that's why it's kind of also practically relevant to analyze these kind of objective functions, because they are indeed used in practice. All right, so our main goal is to prove that this objective function has no bad local minimum. All local minima are global. There's one assumption that I have to specify, but it's not going to be used much in this lecture in the proof, because we are going to sweep some of these things under the rug. But I do have to mention this assumption. It may not sound very intuitive. I wouldn't spend too much time on it, but just let me mention it. So this is called incoherence assumption, and this assumption is necessary. People know it. So we assume that. So I guess we assume, for example, first of all, we assume that the ground truth has norm 1. This is without a generality. We just for convenience fix a scale. And then after you fix this scale, you assume that the ground truth on vector z, so recall that m is equal to zz transpose. So z is the ground truth. So the infinity norm is less than mu over square root d. And mu is considered to be a constant. Or logarithmic in D. So what it's saying is that this vector z, the norm is 1, and also the entries are spread out, right? You cannot just have all the mass concentrated on one entry, right? So the reason why you don't want that is because, for example, a counterexample is that if z is just E1, then your M is just E1 transpose, which is just the top left corner of the matrix. You just have a very, very sparse matrix, and top left corner is one. And then there's no way you can recover this matrix unless you observe that top left corner. So basically all bets are off. You have to see enough entries, right? So this incoherence condition is in some sense trying to rule out this kind of like pathological cases, but I'm not going to talk too much about it. It's just for the formality. Okay, cool. So this is just for the rigorous of the proof. So here's the theorem, and I guess I'm going to stop after I state the theorem and then prove it next time. So the theorem is that suppose P is something like poly mu and log d over d epsilon. Recall that we are in a regime that P is roughly 1 over d, and this is the same regime where epsilon is something like larger than 0, kind of like a constant, and this is a poly factor in mu and also poly log in d. Okay, so suppose P is on this order, and then we assume the incoherence. And then our local of f are what we are. So actually, you can prove that they are all exactly global minimum, but for the moment, we only prove that they are close of square root epsilon close to either z or minus z. And z and minus z are clearly global minimum because the error will be exactly 0. So all right, so that's the statement. And also just to mention, you can also have strict saddle conditions. So you can also have strict saddle conditions. You can also prove that. It's just that I didn't include it just for the sake of simplicity. And you do have to prove that to have the rigorous result. And if you don't prove it, you just prove that all local minima are global. Sometimes you may get somewhat misleading results, right? So I think there's a paper that shows that actually in some kind of like somewhat weird cases, you can show very strong looking results, very like the results like looks very strong in the sense that all local minimum global, but actually the reason why they are so strong is because somehow in that setting you ignore the strict saddle condition, which is problematic. All right, so I guess the proof is obviously too long to cover in 1 minute, so I guess I'll leave it to the next lecture. I can take some questions if anybody has any questions. Otherwise, I think we are good today. Okay, there's a question. Sounds great. So are there any neural network models where these are known to be held? The answer is no, especially if you look for a global property, like globally or locally global. I don't think we have any proofs for any real neural network models. I guess there is a proof for linearized network models, like all the activations are linear. And actually, in that case, if you have more than 2 layers, you don't have the strict saddle conditions. You have a lot of bisaddle points. So basically, the short answer is that I don't think there are any real cases, like satisfactory cases where we know how to prove this. I think they are for 2-layer networks. If you assume some conditions on the input, for example, if you assume that the input are linearly separable, then there is a proof for this. Yeah, and there are a bunch of other cases where you can have some partial results. Next week, in the next lecture, maybe the second half of the lecture, I'm also going to give another result, which is somewhat more general, like it applies to many different architectures, but it has other kind of constraints. First of all, it doesn't really show this kind of exactly this kind of landscape properties. It shows that this kind of properties holds for a region, for a special region in the parameter space. And that's the so-called NTK approach. I'm going to specify more details, but there are also other kind of like problems with those kind of approach as well as, I'm going to talk more about it next lecture.